next speaker is Professor Deep Ray from Department of Aerospace and Mechanical Engineering, University of Southern California. And the topic of his talk is deep learning based posterior inference for inverse problems. So Deep Ray, you can begin your lecture now.
Thank you so much. I would like to. Am I audible on your end?
Yes. You are audible. Yes.
Yeah, so I would like to thank the organizers for inviting me to be a part of this conference in the memory of Professor Vasudeva Murthy. I had the privilege of knowing him as a doctoral student at TIFR, and I'm sure anyone else who knows him would agree that he was a very charismatic, jovial, and inspiring person. And I'm sure that he'll be fondly remembered and sorely missed. So let me begin my talk. So what I'll be presenting today is some work I've been doing recently with my research group at University of Southern California, which is to try and see how you can use deep learning in the context of Bayesian inference. So here is a brief outline of my talk. So I will be basically dealing with inverse problems and particularly those that arise from some underlying partial differential equation. And I'll be talking about how you can solve these inverse problems in the Bayesian context. Then for those who have not seen what deep neural networks are, I'll give you a very brief primer on what these neural networks really are. And then I will talk about a very specific kind of deep neural network, which is known as a conditional generative adversarial networks. I know this is a mouthful, but I'll explain to you what each of these words really means. And then I will show you how you can use these so-called CGANs to do Bayesian inference for PD-based models. Okay, so let's talk about some forward and inverse problems. So let's say we have some forward problem where you take an input X and you have an output Y. And a typical example of a problem that arises from a partial differential equation is, say, the heat conduction equation, where you're interested in inferring or evaluating the temperature field U on some domain at some final time t, given some initial condition U, and also the heat conduction coefficient, kappa, and some source. So the forward problem would be given some initial condition U naught on your domain. You want to determine the final temperature at some capital time t. And you could typically solve this either analytically, or you could use something like a finite difference solver, where I show you here that you start off with some discrete initial temperature field on some 2D grid, and you use your finite element or finite difference solver to get a discrete final temperature field Y. So this is the forward map. Now the inverse map is starting from the final temperature field. You want to infer what the initial temperature field is. And of course, this inverse problem is highly ill-posed, and it becomes even more challenging when we have to deal with noisy measurements, where you're not measuring the final temperature in a clean manner, but there's some inherent noise. In this case, you can't even see the underlying temperature field, but this is what you have to work with. So given this noisy discrete temperature field, you want to infer what the discrete initial temperature field was. So this is the setup that we want to work in. So there are several challenges with inverse problems. First of all, even if the forward map is well posed, the inverse map will be maybe highly ill-posed. You will have to deal with noisy measurements, which is true for most realistic problems. And furthermore, if you have some prior knowledge about the field X that you're trying to infer, in this case, is the initial condition, you want to be able to embed and use this prior knowledge in some meaningful way in your inverse problem solver. And what is also important in when you're trying to reconstruct any such X given some measurement Y is deduce the uncertainty in the inferred X. And this becomes important in applications where you have to make high stake decisions. As an example, say you're trying to solve a medical imaging problem to detect liver lesions, and you start off with, say, some CT scan, and you use a method to reconstruct, say, a slice of your liver, and you give this to the medical practitioner. This is a little unsafe for the practitioner, because what the practitioner does not know is how much to rely on this reconstructed image that you've given the person. On the other hand, if you give the person an inferred field along with, say, a point-wise estimate of the standard deviation showing how much of uncertainty there is in the various regions of the reconstructed image, then the practitioner can take a more informed decision. So UQ, or uncertainty quantification, is also important when you're trying to solve inverse problems. So there are various ways of solving those problems. The one that I'll be tackling is in the context of a Bayesian framework, where you assume that X and the measurement Y are actually modeled using random variables, capital X and capital Y. And then the aim is, given some realization of the measurement, you want to approximate the conditional posterior distribution P of X given the measurement Y. You want to approximate this, and you should be able to sample from it. So this is what I show here in the schematic. So you have some measurement Y, you have some good sampler, which is able to generate a number of samples X from this conditional distribution. And once you have this ensemble of X's, then you can evaluate all sorts of statistics like the pointwise mean, pointwise standard deviation, and you can quantify how well you can, say, recover a reconstructed field for a given Y. Now, the challenge here, of course, is how do you construct this sampler to generate all these ensemble of X's? And this is where I'll be using deep learning. Now, when it comes to evaluating samples from the posterior, a commonly used method is something like a Markov chain Monte Carlo, where you would kind of train a Markov chain whose stationary distribution would essentially be samples from the posterior distribution that you're after. Now, such methods can be very expensive if the dimension of the field that you're inferring, let's call this dimension nx, if it is very large, such methods can be very, very expensive to use. And the second challenge is, suppose you have some prior knowledge about the field that you're inferring. This information might be given in terms of very complicated data. As an example, let's say that you're solving a problem where you know a priori that your X has this microstructure-like profile to it. Or you could be solving another problem where you're told that X is actually these handwritten digits, which is known as the mnist digit in machine learning. So say this is what X looks like, and this is the a priori information you have. Or if you're trying to solve inverse radon transforms, and you're given the a priori information that X actually looks like these so-called phantoms, which represents the human head. Now, the challenge is, how do you represent samples like this using simple distributions like a multivariate Gaussian? You really can't do it. It's quite hard to do so. So what I will show you is that you can use deep learning to resolve both these issues. Now, as I promised, I'll tell you a little bit about what deep neural networks really are. At the mathematical level, a neural network is nothing more than a parametrized map, nn theta, which goes from a domain omega x to a domain omega y. And typically, this parametrized map is formed by an alternating composition of affine transformations followed by nonlinear componentized activations. And each of these affine transformations are parametrized using these parameters theta k's, which are the parameters of your network and are known as the weights and biases of the network. Just to give an example of what would happen in one of these internal layers, say you have a vector of size 4 that is passed through an affine transformation, which is parameterized by W and B, which are the weights and biases, which correspond to the parameters of this affine transformation. And this gives you a vector of size 6. Then to each component of the 6-dimensional vector, you will apply a non-linear transformation, which is known as an activation function, and that will give you a 6-dimensional vector y. And this then will serve as the input to the next affine layer, and so on and so forth. So this way, data is passed from the left all the way to the right in the neural network. And then finally, you get some prediction given some initial input to the neural network. Now, how do you actually use such a neural network? So let's assume you're given some x's and y's, which are rated in some manner. So let's say that the y is equal to fx. So there is some unknown relation f, which you don't know. But all you have are these pairwise samples of x and y's. And just using this data set of x and y's, you want to be able to come up with a neural network that is a good approximation of this relationship between x and y's. And this means you have to somehow choose all these parameters theta in an appropriate manner such that the network approximates the underlying map f. And the way you would do that is by first defining some suitable measure to figure out the discrepancy between what is true and what the network is predicting. So you have this measure on this product space, which essentially measures the discrepancy between a true XY, say, which is coming from your data set, and the XY, where the Y is being predicted by the network. A simple example could be something like the mean square error. So once you have this metric defined, you would define a loss function over the whole data set, which could be an average value of this metric over all the samples in your data set S. And this will be a function of the parameters theta of the network. So once you have this loss function or objective function, you need to solve a non-convex optimization problem where you have to find the theta star that minimizes this objective function. And then this theta star will give you a neural network, which will be a good approximation to the underlying function f, at least on the training set that you've trained on. So these are the network parameters. But of course, when you're training neural networks, you also unfortunately have a bunch of hyperparameters, which would be, for instance, how many of these layers do you have in a network? How big are these layers? What is a suitable activation function that you want? For instance, if you know that the f that you're trying to approximate is smooth, and you want the activation function also to be smooth, then what kind of an optimizer do you want to use to actually solve this non-convex optimization process? How do you stop the optimization because you're doing a non-convex optimization, so you may get stuck at local minima? How do you figure out, how do you get out of local minima? All these are also challenges. What is the suitable loss function? This will depend upon whether you're doing regression or classification. That will change the metric that you're working with. And of course, how do you also construct the data set? Now, unfortunately, there is no rule book that will tell you how to choose these hyperparameters. People typically choose them based on their experience, but under the assumption that you spend enough time to find these hyperparameters and train a neural network that's a good approximation to f, then your job is done, and you actually end up getting very good results in various applications, also in scientific computing. Now, I'll be, of course, talking about one such application where I'll be using a neural network to approximate a conditional probability distribution. So this brings us to this very specific kind of neural network, which is known as a conditional generative adversarial network, or a CGAN. And this actually learns distributions conditioned on another field. Now, a conditional GAN actually comprises not one, but two different neural networks. One is known as the generator G, and the second network is known as the critic, which I denote by D. And because we're solving inverse problems, I will flip the roles of X and Y, where Y serves as the input and X is sort of the output that you're trying to predict. Now, what is the generator network? Now, the generator network takes as input some measurement Y, and it takes as input a latent variable Z, which is sampled from a very simple distribution like multivariate Gaussian distribution. And what's important is that Z has a much smaller dimension than the dimension of X, which you're trying to infer. And say you have a bunch of XYs from the joint distribution, this will comprise your training set that you're working with. So the generator takes a Y, takes a Z, and it kind of generates a fake X that resembles an X that you would hopefully get from the true distribution. Now, what does the critic do? The critic takes as input pairs X and Ys, and whenever it sees an X and Y which comes from the true joint distribution, it assumes a large value. But whenever it sees an X and Y where the X is generated by the generator, it's a fake X, it assumes a small value. So the critic is trying to distinguish between true joint samples and fake joint distribution samples. So the critic and the generator are sort of trained in an adversarial sense, where the generator is trying to generate samples to fool the critic, while the critic is trying to catch the fake samples generated by G. So this is why it's known as adversarial networks, but these two networks are at battle with each other. It's called generative because you're generating new samples from some target distribution. And it's called conditional because you're conditioning it on some other measurement Y that also is an input to the generator. So you have to train this adversarial neural network. And for that, you have to define a suitable loss or objective function. And the objective function that one could work with looks like this. It's a function of G and D. So when I say it's a function of G and D, it's actually the function of the trainable parameters of the network G and the network D. And this is the expectation of the value of the critic when X and Y are sampled from the true joint distribution, which would be, say, your training set, minus the value of the critic when X is generated by the generator and Y is coming from the true distribution. So the critic will actually try to maximize this loss function so as to distinguish between fake and true samples, while the generator will try to minimize this loss function. So you have to solve a min-max problem over here. And you solve this under the constraint that the critic is one Lipschitz. And say you're able to successfully solve this min-max problem and you obtain the optimal G star and D star. Now, a nice thing with the specific objective function that you've chosen is that you can actually show, and this was proven by Adler et al. In 2018, that solving this min-max problem with this specific objective function is equivalent to solving the following problem, where G star is actually going to be minimizing the Wasserstein-1 distance between the true conditional distribution or the true posterior distribution which you're after, and the push forward of this latent distribution PZ by the generator for a given y for a given measurement y coming from its marginal distribution. So what the generator G star is doing is minimizing the Wasserstein distance between the true conditional and the fake conditional. And if you converge in the Wasserstein-1 distance, you will actually have weak convergence of measures, which means that all your conditional statistics will converge. So you don't have a strong convergence of the measure, but you'll have a weak convergence of the measures. So your means, your variance, standard deviation, all these quantities are expected to converge using the conditional GAN. So this is the way in which conditional GAN converges through the true posterior that you're after. Now, so how would you typically use it for a given problem? So here are the steps. So first, you will acquire some samples x1s to xn's from the true prior. So either this is given to you, or this is given in terms of some snapshots or in terms of some constraints, using which you construct this n samples of x from the prior distribution of x. Once you do that, you assume you also have access to the forward map F. So for, say, the heat conduction equation, it's going to be a finite difference solver. So using this forward map F, you will generate a y, and then you will add some noise to it to create a noisy measurement. And this will give you these pairwise samples xi, yi's, which will be your training set for the conditional GAN. Then with these pairwise samples, you will train a conditional GAN. And once the conditional GAN is trained, you will take the generator G star, and you will take some new test measurement y, which was not there in the training set, and you will pass it to the generator G star. And you will take, say, n different samples of the latent variable z, which is easy enough to sample from because it's like a multivariate Gaussian distribution. And for each of these samples of z, you will get a corresponding sample of x, which will represent a sample from the posterior distribution. And then you can evaluate the mean or standard deviation of these ensemble and evaluate all sorts of statistics corresponding to the posterior distribution. So this is how you would use a conditional GAN to generate samples from the posterior distribution and then evaluate statistics with respect to it. Now, to demonstrate that this actually works, I will come back to the heat equation and show you what you would do in that scenario. So I'm trying to solve, say, the inverse heat conduction equation. Of course, the PDE is given like this, which I've shown you earlier. In this case, X would be the discrete initial temperature field on some two-dimensional grid. Y would be the noisy discrete final temperature field on the same 2D grid. The forward map F will be a finite difference or a finite volume solver for the PDE. So here we've used the first order finite difference solver. You could use something else. And we will assume for this example that the heat conduction kappa and the source terms are constant. Okay, so this is the problem setup. And then, of course, to do Bayesian inference, I have to assume some prior on X. So what I do is I assume that X is given by rectangular inclusions as shown over here. So it's a rectangular inclusion where the background temperature value is 0. And in this rectangle, you have a linear profile for the temperature field. And what is random here is the location and size of this rectangular inclusion. So this is my prior that I have on X. And I interpolate this on a 28 × 28 grid. And then with this kind of an initial condition, I use the forward model to get the clean temperature field at some final time t. And then I add a bunch of Gaussian random noise to it to get the noisy measurement y. So I'll have to work with these XY pairs to train the GAN. So we never actually use the clean Ys to train it. Once you've got the noisy measurement, you throw away the clean Ys. You don't even have this in practice. So we used around 8,000 XY samples to train our conditional GAN on this assumption of prior on X. And once you've trained it, now we will show it a new measurement Y, noisy measurement Y, which wasn't there in the training set, and try to see how well we are able to infer the underlying X. So this here is a new measurement, which was not there in the training set. This is the ground truth X corresponding to this measurement Y. And since this particular prior is parametric, because we can actually, it's basically parameterized as 4 random variables, which correspond to, say, the bottom left corner of the rectangle, the top right, and the top right coordinate of the rectangle. So using 4 random variables, you can parameterize this. In this case, you can actually, using Monte Carlo simulations, generate a reference mean and reference standard deviation for this particular prior. And this is what the reference mean and reference standard deviation looks like. And then what we do is we train a conditional GAN, and we have the freedom to choose the dimension of Z. So Z could be any dimension. Hopefully, it's going to be much smaller than the dimension of X. So what I show here are the resultant means and standard deviations that you get with the conditional GAN for a GAN which is trained with Z having dimension 1, 2, 3, 4, 5, 10, and 15. Sorry, is there a question?
I request the participants to mute their mics. Shrikant, can this be taken care of?
Okay, shall I continue?
Sorry, there was
no worries, no worries, no worries.
Okay. Yeah, please carry on.
Yeah. So we trained GANs with different dimensions of Z, and what we found is that even when you use Z to be just one dimensional, you actually do a pretty good job at approximating the reference mean and the reference standard deviation. Of course, for this particular problem, we found that Z3 actually gives you the best results, but the point is, with a much lower dimensional representation, you're able to capture the statistics of the posterior that you're after. But this is a parametric prior, and it's a simple enough prior. Now let's move on to a prior which is non-parametric and more complicated. So what I now assume is that the initial condition is actually given in terms of handwritten digits. So the background temperature field is 0, and wherever you see this handwritten digit, the temperature field is actually taking the value 4. So you have these various handwritten digits, which are known as mnist digits, which is the prior from my initial condition. Again, I use the forward model to get the clean final temperature field, and I add a bunch of noise to get the noisy measurement Y. And I train a GAN on these 8,000 pairs of X and Ys, and then I test it on a new measurement, which has not been seen in the training set. And of course, in this case, since it's a non-parametric prior, we don't know what the reference mean and standard deviation are, but we can compare it with the ground truth, which we have for these new test measurements. And we see that this is the ground. So in the second column, you see the ground truth values. The third column, you will see the means from the sample generated by the conditional GAN. And the fourth column is the standard deviation. And you see that we are actually able to recover the underlying digit that gave rise to the measurement. What you'll also notice in the areas that I've marked with this red rectangle is that in these areas, the mean seems to deviate from the ground truth value. But what you will also see that is in these exact same regions that the standard deviation also takes a very large value. So standard deviation peaks along the edges of the digits, but also in these red regions where we seem to be deviating from the ground truth. So this is another advantage of using uncertainty quantification, because the standard deviation in this case serves as a good metric to also measure the error that you're making in trying to recover the underlying X. Here, for instance, you can see that in the ground truth 5, there is a disconnected branch on the top, but the mean seems to have a connected branch. But again, the standard deviation is high there, saying that in this region, you should not trust the reconstruction as much as you do in other regions. So this is a more complicated prior, and it works. Now, I want to answer another question here. What happens if you now try to use the same GAN trained on these mnist or these handwritten digits on a very different kind of measurement, which doesn't look anything like a digit. And this is the question of generalizability. So by definition, we say that a network trained on a set A has good generalizability if it gives good predictions on another distinct set B whose samples are sampled from a different distribution compared to those which are lying in set A. So if it's working well beyond the training set A, it is said to generalize well. So it's almost like saying that you're trying to approximate a function and you have an interpol, you're creating this function, or you're approximating is using some interpolated values. You want to see how well it does in other values at which you've not interpolated at. So this is a one way of analogous way of understanding what generalization is. Now, this is typically hard to do, and networks are known to interpolate poorly. But for this conditional GAN, we were able to prove a theorem about generalizability, details of which are available in our preprint. But I will just highlight the major themes of this theorem, or what it's trying to say. So it's saying that we make three assumptions. First of all, the inverse map, of course, may not even be well defined, but let's assume that the regularized version of the inverse map is well defined and that it is spatially local. By spatially local, what I mean is, if you look at, say, the X that you're trying to infer, and you look at, say, a small spatial patch of X, then it locally depends on a patch of Y, which is in the neighborhood of the patch of X. So there's a local dependence of X on Y. So we assume that the regularized inverse map is spatially local. Now we assume that we have two sets A and B, which might have very different looking elements, but they share a commonality that they have similar local spatial features. If you zoom into a small area, they will look like they have similar spatial features. And third, we train a conditional GAN on set A, and this conditional GAN is also spatially local. Then under these three assumptions, the conditional GAN will actually generalize well to the set B, which means it will actually give you good results on set B, even though it contains very different looking samples. And I will illustrate this with an example of this heat equation that we were trying to invert. So this is the conditional GAN that was trained on these handwritten digits, or the mnist test set. And now we are testing it on something known as not mnist. I mean, it's maybe not the most interesting looking name that has been given to this data set, but basically it contains of characters and letters in different fonts, but these are not handwritten digits. So this would be the corresponding measurement. This is the ground truth, and this is the mean and the standard deviation from the conditional GAN trained on mnist. So what we see here is we are not actually recovering handwritten digits. We are actually able to recover the underlying character in these specific measurements. Of course, it's not as good as what we had in the training set, but we still get pretty decent reconstructions, even when we are looking at something which is very different in shape. But the important feature here is that the not mnist set and the mnist set have locally similar features, which means if you look at any small region of, say, X, you will find that it is a two-valued function, and it essentially is composed of lines or simple curves. So at the local level, they look very similar, but of course, the global features are quite different. So this is one of the assumptions in this theorem, that the set A and set B should have the same local features. But we also have these other two conditions, that at least the regularized inverse map should be invertible, should be spatially local, and that the conditional GAN trained on set A, which is the mnist set, should also be spatially local. So I will also demonstrate that numerically over here. So what I look at is a localized version of the inverse heat equation, and try to show you that this actually is a regularized version of the inverse heat equation, and I'll show you that it is actually local. So we take a final temperature at time t is equal to 1, given by a Gaussian bump centered as S0. And this is, say, for instance, an S0 which is centered at 0, 0 in the center of the domain. And then you solve the inverse heat equation using fast Fourier transform. But since this is highly ill-posed, you'll have lots of oscillations. What you can do is you can kill the higher modes of this approximation, which is also known as hyperdiffusion, and recover an initial condition from this problem. And this is what the corresponding initial condition would look like for this final temperature field, which essentially kind of steepens up as you move backward in time. So the regularized inverse heat equation can be solved. And now I will show you that this in fact is local in nature. So what I will do is I will look at the solutions solved backward in time for different locations of this center of the Gaussian bump. So I will move this in a 28 cross 28 grid, and I will look at what the temperature field looks like at the initial time, T is equal to 0. So I look at the initial temperature field at a given location in space S1. So let's focus on this plot over here. This red pointer marks the location S1 that I'm concentrating on. And then at this fixed location, I will look at the value of the initial field as I move the Gaussian bump at the final temperature in a 28 cross 28 grid. And what you will see here is, so these are all the values for different locations of S0. And what you see here is, if the S0 moves away from this red dot, the value of the temperature field goes to 0. But when you approach this red mark, then the temperature actually becomes prominent, which essentially shows that the influence of UST on the initial temperature US0 weakens as the Gaussian bump moves away from this S1. And this is not specific to just this location. You look at any other location in space, S1, and you see the similar trend. So there is this local dependence of US0 on UST on US0. Now, I also want to show now that this is the local dependence for the regularized inverse heat equation. What about the conditional GAN? Is that also local in nature? So to see that, so the conditional GAN takes as input, say, a measurement Y, which is a 28 cross 28 image, and gives you an output, which is also a 28 cross 28 image. So you look at any one component of the output, let's say the kth output of the generator, and you take the gradient of that with respect to the input Y. So this will also be of shape 28 cross 28. And here I show you what the gradient looks like for the kth component is shown in red over here. And the various locations here, so say this location will be the derivative of this component, differentiating the kth component of G with respect to the component of Y at this location. And what you see again here is that the gradients are concentrated whenever you have Y is at the same kth location as the red marker. And as you move away from this marker, the gradient seems to decay. So there is again this locality of G star that you can recover by taking these gradients of the generator. And because of these three conditions holding, that is that set A and set B have similar local features, the regularized inverse map is local in nature, and the conditional GAN trained on set A is also local in nature, we're actually seeing good predictions of the network on set B. So we have good generalizability. So with that, I reach the end of my talk. So what is it that we actually gain by using this deep learning strategy? First of all, you're able to capture and represent complex prior data. So it could be something like a digit. It could be something, we've looked at different kind of problems where where the prior is given in terms of maybe ellipses, which are used in CT scans. It's given in terms of microstructures, which is used in structural PDEs. And it does a pretty good job at capturing complex prior data. Secondly, for most of these problems, the dimension of X can be as large as 10,000, 100,000, but the dimension of the latent variable Z, which you're using to sample and create samples of X from the posterior distribution, can be as small as 50 or 100. So you have a significant reduction in dimension. Of course, this works under the assumption that there is a lower dimensional representation of your posterior distribution. If that doesn't exist, maybe this NZ will be as large as NX. But in most problems with an underlying structure, we do find that there is a lower dimensional representation of the posterior that you're trying to approximate. And the advantage here is you don't need to do any markups in Monte Carlo once you've trained the network. It's very easy to sample from the trained conditional GAN, and you can easily compute any statistic that you want using empirical averages. And I've also shown you that we have, under certain assumptions, we can show that this network will be able to generalize well to other data sets. So what this would mean is you can train on a much smaller data set, which makes the training more efficient and quicker, and then you can still get good results on samples lying far outside this data set. And this algorithm has been tested on several other PDs, which you can see in our preprint, but we've also tested it in other physics-based problems and several medical imaging problems, and we're getting very efficient results or performance with this conditional GAN approach. So with that, I will end my talk and I will answer questions from the audience if there are any. Thank you.